Hello, everybody. I want to start off by welcoming you to the Congress of the World Federation of Societies of Anesthesiologists. And I want to also thank Fresenius Kabi for the opportunity to speak to you today. They invited me to speak on a subject about which I'm fairly passionate, although I don't claim particular expertise in this area. And that is talking about our role as anesthesiologists in looking out for the environment. And I'm going to introduce you, if you don't already know about it, to this concept of life cycle environmental costs of anesthetics. I am a professor emeritus at the Department of Anesthesiology at Stanford University, the adjunct associate professor of bioengineering and therapeutic sciences at UCSF, and currently I'm the editor-in-chief of the ASA Monitor. So I want to go back to dinner that I had back in 2005 with an anesthesiologist, Marie Chetta, shown here, and her husband. Her husband is John Doyle, and John Doyle is a mathematician primarily. He's at Caltech, the California Institute of Technology, and he's the Jean-Louis Chameau Professor of Control and Dynamical Systems, Electrical Engineering and Bioengineering. And we got on the subject in 2005 of climate change and global warming. And John said the following to me during this dinner. He said, I am a climate change skeptic. The models are all wrong. The published models do not account for positive feedback systems. For example, the release of methane when permafrost thaws accelerates global warming. These positive changes are critical to understanding where climate change is taking us. The reason I'm a skeptic is that climate change will come sooner and it will be more severe than the published models predict. I've thought about this dinner and this conversation almost weekly since we had it, because what he said is absolutely proved to be true. And we've seen it accelerating. Just in the last week or so, the Intergovernment Panel on Climate Change released their 2021 report. And quoting from it, recent changes in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. Human influence is the main driver of hot extremes, which have become more frequent and more intense. Ocean warming since the 1970s and ocean acidification. Changes in the frozen areas of the planet. There's a global retreat of glaciers over the last 30 years, 40% decrease in Arctic sea ice since 1979, decrease in spring snow cover since the 1950s. Well, just look at our last week here in the United States. Hurricane Ida went through. Quoting from the weather.com, it was one of the strongest hurricanes to ever hit the US mainland. It caused catastrophic damage in its path. Here in California, we have the largest fires and the worst fire season we have ever had. Our forests are literally burning down. Lake Tahoe, a wonderful resort, is threatened. The Colorado River is decreasing in its output. And for the first time ever, there have been water cuts in the cities and counties that depend on the Colorado River for their supply of water. And that's just in the last week. You look at the floods in Europe, the fires in Turkey. It's happening exactly as John Doyle said it would, faster and more severe. So you and I have a role here because everybody has a role here. And I want to thank right from the start, Forbes McGain. Forbes McGain is an anesthesiologist. He practices in Australia, primarily in the area of intensive care. But he has been passionate about this area. And most of what I know about the subject, I learned from Forbes McGain. And he said, during one average working day, an individual anesthesiologist administering nitrous or desflurane contributes the CO2 equivalent of driving 1,000 kilometers or 620 miles if you're in North America. One day, it's like you got in your car and drove 1,000 kilometers if you're using nitrous or sevoflurane. Annually, worldwide, anesthetic gases are estimated to have the same global warming potential as 1 million American passenger cars. I mean, that's a lot. Every day of the year, every day, the United States operating room staff deposit more than 1,000 tons of rubbish every day, 1,000 tons of rubbish. And actually, anesthesia practice is likely to contribute a quarter of the total. When I see them wheeling these dumpsters out of the OR, I think our contribution may be less than that, particularly for our total joint replacements. So we're going to talk about life cycle assessment. And what is life cycle assessment? Life cycle assessment takes a look at the impact on the environment. And it's called cradle to gate to grave, or more commonly just cradle to grave. Cradle is the birth of whatever it is that you're using. Aspects of cradle include looking at the cost of just digging up the materials that you make of it, or recycling it, or whatever that process is to extract the raw materials. You have no idea, by the way, about the huge environmental cost of this thing. The raw materials come from China in a specific place that is one of the only places that allows the mining of rare earths. Then you have to manufacture it, which generates a certain environmental impact. First the materials and the manufacture of the product. Then you have to transport the product and the costs associated with transportation. And then here's the gate. The gate is where you and I operate, because we make the decisions about taking a product from the shelf and using it clinically. And then from the gate, it goes to its end of life. If we're lucky, some of it can be recycled, but that which can't be recycled winds up being tossed out, contributing to landfills, and also exerts an environmental cost. So that's life cycle assessment. And if you want to know the environmental impact of what we do, you have to approach it using life cycle assessment. So again, raw material acquisition, manufacturing, transportation, distribution, inventory, shelf life. If something has a shelf life of just a couple hours, it's very different from something that has the shelf life that's indefinite, like some of the donuts you can buy in California. How the product is used, the cost of recycling, if that's even possible, and the disposal. And you have to look at the disposal integrated over literally decades, during which the product may be leaching toxic chemicals into the environment. So let's take a simple plastic water bottle. And I suspect some of you may have them sitting on your desk right now. The cost of acquiring the plastic is considerable. It comes from oil, as you likely know. There's a process called melt polymerization that requires a lot of heat that generates carbon dioxide, just the generation of energy. Solid state polymerization, injection molding, blow molding. Then finally, it's transported and gets to consumers. The waste gets dumped out. Some of it gets recycled. A lot of it goes into the grave. This is cradle and grave for a plastic water bottle. And this has been studied extensively. And the actual amount of research that goes into this is sizable. Here you can see, they look at the minerals that are used in fertilizer. This, by the way, is producing plastic water bottles from sugar cane. You might say, well, gee, isn't that great? But you still have all these processes, all of which use energy and introduce carbon dioxide or carbon dioxide equivalents into the atmosphere. And then they assess for the plastic water bottles how all of these environmental aspects are affected by different means of creating plastic water bottles. Well, to start with anesthetics, we have to start at the elephant in the room, which is the greenhouse gas potential of our inhaled anesthetics and nitrous oxide. This is a study by Dr. Silbeck Anderson and his colleagues. I point out that these are rocket scientists. They work at the Jet Propulsion Laboratory, which is run by the California Institute of Technology. And he looks at isoflurane, desflurane, and sevoflurane. the smog chamber, Fourier transfer, infrared. I can't even read this abstract. I mean, these papers and this work is so technically complex. It's unbelievable, but I can certainly jump to the punchline quickly. And by the way, I've had extensive communications with him because when I was editor-in-chief of Anesthesia and Analgesia, we had an entire issue on this topic of global warming. And he just says, look, the atmospheric lifetime of isoflurane, 3.2 years, desflurane, 1.1 years, sevoflurane, 1.1 years, but desflurane hangs around a long time, 14 years. Radiative efficiency is basically how well it reflects back to the earth. Desflurane reflects the heat back to the earth quite well. The 100-year global warming potential, SIVO is 130, and this is units of carbon dioxide versus units of carbon dioxide for desflurane. And if you adjust it to the MAC of the drugs, per unit, SIVO is 260, and desflurane is basically 13,000. So desflurane we should simply stop using, period. Now, Dr. Jody Sherman is one of Dr. Forbes McGain's frequent collaborators. Dr. Sherman contributed an article for the same issue of Anesthesia and Analgesia, where she asked, what is the cost of manufacturing, transport, drug delivery, and waste management for desflurane, isoflurane, sevoflurane, and propofol? And this right here looks at the grams of CO2 per hour of anesthesia. And in terms of grams of CO2 per hours of anesthesia, desflurane is expensive to make. It's hard to make compared to ISO and SIVO. Then there's the transport. The use of it is also considerable because the vaporizers have to be heated and pressurized, as you know. So the cost of manufacturing desflurane is considerable. But this leaves out the waste gas effects of desflurane. When you add in the waste gas effects of desflurane, we go up literally an order of magnitude in CO2 equivalents. That's why I say this is the elephant in the room. If you're going to combine desflurane with nitrous, this is the effect of desflurane here in the pink, and the red is the effect of the nitrous. In the case of sevoflurane, because of limitations, at least in the US label for sevoflurane of 2 liters a minute total gas flow, it has twice the nitrous effect. So this is the additional nitrous oxide to it. And this is crazy. This is per MAC hour of anesthesia, 50,000 grams per MAC hour. Okay, well, that's hard. That's a hard unit for me to get my head around. So what I've added here is I've translated this into kilometers driven. An hour of desflurane nitrous anesthesia is the equivalent to getting in your car and driving 375 kilometers. That's enormous. Propofol obviously has no anesthetic gas effects. And if you even go back to the previous slide here and look at the manufacturing cost of propofol, it's trivial. Propofol is a solvent. You can actually order propofol literally, I mean, not as the emulsion, but just as the solvent. You can order it in gallon or ton quantities from chemical supply companies. So propofol is cheap to make, and it almost has no greenhouse gas effects here at all. So then let's take a look at cradle to grave greenhouse gas emissions for 20 anesthetics, because we don't have remifentanil in here and fentanyl in here. Again, Dr. Sherman is part of this work. And they went and they did complex models, because, by the way, for the most part, these data aren't available, and they added remifentanil to the mix. And fentanyl, all these commonly used drugs, dexmedetomidine is kind of expensive to make, succinylcholine relatively inexpensive to make. But per gram, that's a lot, by the way, per gram of the drug itself, dexmedetomidine, the most expensive, is equivalent to driving your car 8 kilometers. Remifentanil per gram of drug is basically 1/10 of that, or driving your car about 1 kilometer. But that's per gram. If we do a little math, I'm not going to take you through the math in the interest of time, but if we do a little math, the amount of remifentanil, if you're just going to draw up a 2 milligram vial, and that's usually what we would usually open at Stanford for a case, a 2 milligram vial, the environmental cost of that all in is about 1 meter of driving. 1 meter. It's trivial. So going back to comparing our anesthetics for greenhouse gas effect, SIVO, ISO, DES, all of these, considerable cost to manufacture. Propofol is almost nothing, and remifentanil is even more nothing than propofol. And part of that's because of the potency of remifentanil. It's so potent that it's cheap to make. And you look at the greenhouse gas effects, these don't even show up on the list. I have to tell you that I'm a big fan of propofol nitrous, and in preparing this lecture, unfortunately, I'm going to probably change my practice to just Tiva, as much as I think propofol nitrous is a great anesthetic. This was a paper that came out talking about nitrous oxide by a group published in the BJA that looked at the role of nitrous, and they say virtually nothing about nitrous other than to kind of dismiss it. Based on U.S. Environmental Protection Agency authority, medical use of nitrous is estimated at 1% of global nitrous. So in other words, physicians, we only add about less than 1% of the total nitrous pollution, most of which comes from agriculture and other uses. So they kind of blow it off. And not surprisingly, Forbes McGain wrote back and said, you guys are wrong to blow this off. A 50% mix of nitrous oxide and oxygen, I use a little bit more nitrous when I usually use 70%, but nevertheless, with a fresh gas flow of 1 liter per minute, comes out to driving a European car 120 kilometers for one case, lasting 1 hour. As a profession, we should not neglect the greenhouse potential of driving 1,000 kilometers during an 8-hour working day. So if you're using nitrous, as I commonly do, it's like getting in my car and driving 1,000 kilometers. Do I really need to do that? He also points out in this reply to this letter, the NHS Sustainable Development Unit carbon footprint for anesthetic gas use. So get this, total emissions for anesthetic gases, including nitrous, is 2.5% of the UK greenhouse gas emissions, according to the NHS. And half of that comes from nitrous oxide. That is much more than I would have expected. So the long-term plan from the National Health Service is to reduce the carbon dioxide equivalents of our inhaled anesthetic practice by 210,000 tons per year. Volatile anesthetics is half of that. Nitrous in the OR is half of that. And there's even more nitrous outside of the OR. And I believe it's because nitrous oxide is popular in both the ER and in obstetric practice in the United Kingdom. That's not the case in the US. So Forbes McGain and his colleagues here, an international group, by the way, if you look at where they're from, a reduction in the carbon footprint of anesthesia can only be achieved by significantly reducing the use of nitrous oxide. So I'm going to stop my presentation here. There's more in the presentations available online, but in the interest of opening it up to chat, I would like to go back and say that if you want to do the right thing, actually, I'll quickly go to this thing right here. Avoid inhaled anesthetics. Certainly stop using sevoflurane entirely. Run your flows as low as possible. And because I happen to like Tiva anywhere, after preparing this talk for all of you, I'm going to change my practice. And I have to write back to Forbes. He'll be pleased to know this. And I'm just basically going to stop using nitrous and go propofol remi for pretty much everything. Because it's up to us to change the environment. So with that, I'm now going to open up the chat and see if there are any questions. All right, so anyone with questions, you have a minute to type your questions in, and I'm more than happy to answer them. And by the way, I will say that if you want to write to me, while I'm waiting to see if any questions show up in the chat, I will add one more slide.
Maybe I'll just give you a question here, Steve. That was great.
Yes.
It was a great talk you did. Thank you very much. So I wonder, isn't there any disadvantages by throwing away the usage of the gases? Like you have to dispose of all the vaporizers, and I don't know, are there any physiological, are there any disadvantages for the patients? I mean, if sevoflurane, desflurane, isoflurane almost disappears out of the operating room.
I don't think that's a good question. And in the seconds I have left here, oh, by the way, write to me if you want copies of my slides. Anybody? But Eric, yes, I would not advocate taking them off the anesthesia machine. I think nitrous should be left on the anesthesia machine for some reasons, and I actually think that these drugs should. And certainly there are cases like if you have a patient who has, status asthmaticus, the only way you may open up the lungs is with sevoflurane. there are reasons to keep these drugs there in some patients. Children, you can't start an IV. You need to do inhaled inductions. But in general, we need, I think, to switch to total intravenous anesthesia. And certainly I'm going to do that. I think I'm out of time, but I'm happy to take any other questions. Otherwise, thank you, everybody, for their time and attention today.
Thank you, Stephen.
Thanks, sir.
Stephen, this is Christian speaking. I have one question. If
Yes.
more hospitals changing more to TIVA, then as well they might need different pumps. So this as well has to be included in the life cycle of the anesthetic routine, no?
Oh, that is correct. And in theory, but I don't actually recall seeing it, but one needs to include the administration costs in life cycle assessments. So that would include the manufacture of the tubing that we use to give the drugs. That would include the manufacture of the disposable syringes, and certainly the pumps and the electricity in the operating room. I know that if you look back at Dr. Sherman's article in Anesthesia and Analgesia in 2012, those were factored in. The electrical use in the operating room is trivial. Yes, there is absolutely a cost of manufacturing the pumps, but amortized over a typical service life of 5 years and probably 10,000 anesthetics, the contribution of the pump itself per anesthetic or per hour of anesthesia is quite trivial. So these things all have to be included, but but nothing comes close to getting in your car and driving 120 kilometers per hour.
Is there, by the way, is there TIVA already released in the US? Is it?
So the question about TIVA in the US, TIVA.
TCI, more or less, TCI.
Thank you, yes. TIVA is certainly released. TCI is not released. This remains one of my abiding hopes. I hope to finish it while I was a professor at Stanford. Now I hope to finish it while I'm an emeritus professor at Stanford, which basically ends when I pass away. So hopefully I have a couple of years to keep working on it. But that does remain one of my unfinished dreams, is bringing the United States up to the status in Europe and elsewhere in the world when it comes to TCI.
Thanks, Stephen.
And when do we go to? Do we actually go to 7:40 to 7:45? That's Pacific time. Or are we, when does the session actually end?
I mean, it is supposed to end, but if you have, if there are any more questions, you can still continue. There's no problem with that.
Excellent. No, I'm happy to stay for questions, and I see, oh, by the way, I see questions in the chat. So let me just go to the top. Why isn't there more recycling in hospitals? And the answer is recycling is difficult. And I can tell you right now, we have programs about recycling. We try to get people to recycle everything that we can. But it's quite difficult. Someone asked about charcoal filters. Charcoal filters can capture the inhaled anesthetic gases to prevent them from being released into the atmosphere. After they're captured in charcoal filters, they can then be destroyed, and basically by essentially burning it, and not releasing the raw anesthetic into the atmosphere. There is a cost to doing it, and I don't know, it simply isn't popular. Are the bottles of remifentanil and propofol included in the calculations? The answer is yes. The actual cost of the glass processing, including heat and everything, was included in that process. If we wish to distribute the presentation, you can. If you open the chat and click, and you can click and share it, I will try to do that. Hello, Carolyn. If we go to TIVA, we need BIS with disposable stickers to monitor anesthetic depth. I agree with that. I basically put a SED line or a BIS on every patient. I find it's more information regardless of the anesthetic technique that I'm using. And I just don't know why any anesthesiologist would choose less information versus more information. So I didn't think to mention that, but I agree. I monitor the EEG with a monitor in literally every patient. There is no need to hurry. That's good news. What do you think about anesthetic gas recapture technology? It does exist. And I will actually quickly go back because I have a slide that I went over in the interest of time on that subject. But if I can go back, and let me move my chat off the screen. But here's an example of this. Let me go forward again, or did I take it off? Oh, I took the slide off. I apologize. Anyway, By the way, if you don't know who the Rolling Stones are, this slide won't make sense to you. I do think we need to start worrying what kind of world we are going to leave for Keith Richards. Rolling Stones fans will understand that. But gas anesthetic recapture technology absolutely exists, and it's actually simple. There are these things called reflection filters that keep the gas in your circuit so that you don't have to keep introducing the gas into the circuit. They keep the gas in the circuit rather than going through the pop-off valve and out the waste scavenging systems. These exist. I really don't know why they're not more widely used. Nitrous cracking. I've looked at that. Nitrous cracking, actually, because I thought this would be a great idea. There is a device that's available only, I believe, in the Netherlands for it. It actually requires a ton of heat. So this device does exist. It's basically cracking it. It's heating it. And when you heat nitrous hot enough, it breaks down into nitrogen and oxygen, as you might expect. I was hoping it could be made simple and inexpensive. It doesn't seem to be easily available. Baxter claims they can reclaim the gas from the canisters and it will be reused. That would be great. And all of these things are absolutely worth doing. So I have clinical reasons besides the environment that I use total intravenous anesthetics. And if you use propofol instead of the inhaled anesthetics, a lot of it has to do actually with my wife's research involving inhaled anesthetics and nicotinic receptors. Blocking nicotinic receptors proves to be a bad idea during anesthesia, and that's a whole nother discussion. But nitrous oxide does not. It's an NMD antagonist, so clinically I like nitrous oxide. It also comes off faster than even remifentanil. But I'm going to change my practice because each of us needs to do what we can do. I will attempt to add, actually, I can't do it because of the way my screens are set up. So just write to me. I will just add my email address into the chat here. And I'm more than happy to send you the talks. But if you really want to go to the original source, just go on to PubMed and look for Forbes McGain.
Hi, Steve. Just one question.
Yes.
Great to see you again.
Hi.
What about how do you deal with the propofol waste at
Okay,
Stanford?
excellent question. So first, I will say we're moving to more and more single-use items. I agree with that. That is a problem. Forbes McGain has a wonderful article looking at single-use versus multiple-use. It actually has to be done on a case-by-case basis. There is no global right answer because reusing items requires steam sterilization. That can also have an environmental cost, and it kind of depends on where you get your electricity from. If you get your electricity from coal, you might actually be better off with single-use items. If you get your electricity from wind energy, you'll be much better off with reusable items. So that's a case-by-case basis. I urge you to look at the actual paper from Forbes McGain. There are several of them on the subject of reusables. On the subject of propofol waste, it is a concern. I will tell you that propofol being discharged into things like waterways is shown to have demonstrable effects on fish. Basically, you know, they get partially anesthetized. Propofol is a phenol. I will tell you that is not an issue. It's a hindered phenol, and it does not behave like a phenol. If it behaved like a phenol, we would be killing our patients rather than anesthetizing them. So, but nonetheless, the solvent properties of propofol remain biologically active, and we should try to capture it and not just toss it down the sink. And another question about the need for processed EEG monitoring, and as I mentioned before, I put a BIS or SED line, and Eric, maybe I'll start using your device on literally every patient. And so I personally feel like we should be monitoring the EEG, and I don't understand why there's resistance in our profession for doing it. The cost of the device itself, amortized over thousands of patients, is trivial, and the cost of the individual leads from the greenhouse gas effect is not exorbitant. In fact, it's pretty modest. I haven't seen that, and that's a subject that I might want to ask somebody like Forbes to do it. But we certainly know, like the EKG electrodes and things like this. You know, these are not expensive to manufacture.
Thank you, Steve.
Thank you, Eric. By the way, I do think the question about what we do with propofol, yes, we really should not be tossing propofol into a landfill. Propofol should be captured. And actually at Stanford, we're now doing that. We're asking people to squirt their propofol into a special bucket. And also their narcotics, their opioids into the same bucket. Stanford may just pour it down the sink when we're done. I really don't know what they do with it. But I think they're trying to be responsible.
Don't you think we need to try a bit more to optimize the delivery or the dosing or in order to avoid this this waste? So optimizing how we dose the single unit, how we use it, and so on. That should definitely be a way to forward for reducing this waste.
And as an example of that, I'm going to switch over to using syringes. Oftentimes I use the roller pumps, and I have tubing that is designed for our roller pumps. The problem is that tubing, it takes 20 cc's just to prime it. So 20 cc's is guaranteed wasted out of every bottle of propofol that I run through it, which is a lot of propofol. So if I use the syringe pump, the tubing itself holds just 1 cc. So I will very likely, using 2% propofol, a better ecological solution, probably not. 2% propofol hurts quite a bit more than 1% propofol. And so there's ways of doing this without compromising clinical care. So I really do think that if you switch to TIVA from inhaled anesthetics, you don't compromise clinical care. The only place, by the way, I was asked about the use of inhaled anesthetics, there is some data for cardiac anesthesia that if you use an inhaled anesthetic, they have more myocardial protective effects than intravenous anesthetics. So again, we might want to keep the use of our inhaled anesthetics available for patients on cardiopulmonary bypass. Like I said, so there are, one has to also keep in mind that, we're there to take care of the patient. 2% propofol would cut down on the cost to package it in the plastic, in the glass bottles, and the cost of transportation. But because it hurts more, every patient's going to get yet more lidocaine from me to cut down on the pain on injection. So I wouldn't be a fan of that. It does indicate, by the way, the problems of that one has with everything's a trade-off. If you switch to remifentanil and propofol as your primary anesthetic technique, then you have to ask about the cost of the EEG electrodes. I agree, everything's got trade-offs. If you switch to 2% propofol, we're trading a more efficient way of packaging and delivering the product versus increased pain on injection. My other concern, by the way, about 2% propofol, and I think it's actually banned at many hospitals, is simply the risk of drawing up the wrong strength. I think having 2% and 1% propofol formulations in your anesthesia cart is a potential disaster. Somebody has been using 2% propofol. Excellent. It's propofol. I suspect it works just fine. By the way, to the person who's using it, Renata, where are you? Because I don't think it's actually been licensed in the United States.
Hello, hi, can you hear me?
Yes.
Hi. I practice in the UK.
Okay. All right, I didn't know 2% was available there.
We've been using it for quite a long time for TIVA without problems. It's correct that it hurts, but you can mix it with a bit of lignocaine, the first dose when you start using TIVA, or you can prime the line with a small amount of lignocaine, just like a mini Beers block.
Yeah.
And then
I will tell you that I do neither. Instead, I drop 100 milligrams of 1% lidocaine, which is 10 cc's.
Exactly. Yeah.
And I start every case by slowly. You have to you have to have like a little river going through the vein to have enough contact time with the sodium channel blocker and the lumen of the vein. But nonetheless, I start every case with 10 cc's of 1% lidocaine. And literally nobody complains of pain on injection. It just doesn't happen when I'm the anesthesiologist.
Yeah, so there are ways around it. But the good thing about 2%, if you have a longish case, that it saves you time on changing the syringes. Otherwise, it's just a non-stop syringes changes if this is 1%.
Yeah.
Thank you.
Thank you for that. All right, do we have more questions?
It's Martin. Stephen, just a question.
Yes.
What would you suggest to launch TIVA in the US, or to make it more acquainted, also the use of TIVA first before TCI might be there? would you suggest any kind of training programs to make people more aware of the advantages, or which kind of clinical recommendation would you have?
Personally, I really think, I think first and foremost, we have to get TCI in the United States. TCI makes TIVA really, really attractive. And teaching TIVA with TCI versus teaching TIVA without TCI are very different things. If we can get TCI into the United States, I will tell you that in the United States, people are very concerned about the environment. If TCI could come into the United States, I think that anesthesiologists, driven just by the environmental concerns of the gases, would be happy to switch. It's just that without TCI, a lot of my colleagues simply don't know how to do it. It's hard to know. I mean, I will tell you, a wake up from propofol Remy is just great. As those of you watching this who use TIVA know. And so we can make it much easier. The challenge that TCI or TIVA has is the challenge of the plumbing versus just reaching over and turning on the vaporizer. Reaching over and turning on the vaporizer is effortless. It takes a little bit of time to drop and prepare TCI. I think if somebody could pay a little attention to that, and an example of doing it right was the design of the Sedasis system. The Sedasis system had a basically a little spike that you just simply took your amp of propofol and just put the spike down on it, and it automatically ran the line through exactly enough to prime the line. So all you do is bring it in and hook it up to the patient. If you could do that with TCI, and you can, you could make it truly effortless, just the same equivalent as it is right now when I do TCI, because of the amount of plumbing that I have to put together and running the lines through and programming the infusion pumps. It takes about 3 or 4 minutes. It really needn't take more than 30 seconds with a thoughtfully designed combination of a device and a very efficient disposable.
Thanks a lot also for the great presentation.
Oh, you're sure welcome. So I'm happy to stay with for more presentations. And if Eric, you have the link to my presentation. I sent it to you by email. Could you put that in the chat box for me? The problem is that I have one screen, and if I go to find the link on my email, but could you just paste the link I sent you last night?
Yeah, I'll just.
That's a publicly available link to my presentation. If you could put that in the chat box.
So while I look for it, Steve, maybe so you still think TCI will be available in the US one day? Then there's still people working on it, or that we could in a foreseeable future will be possible?
I think it absolutely has a future. It has to have a sponsor. I can't, it's a TCI pump is not going to be manufactured by Stanford University. So no matter how much research we do, a commercial company has to get involved and actually drive the program forward, because we can do the academic piece of that and the educational piece of that, but we don't actually manufacture hardware. But with an appropriate sponsor, yes, TCI I think will absolutely happen, and I think it can be game changing if the sponsor approaches TCI as basically trying to create something that is as simple as just cracking open a infusion pump. But that's possible, because that's what Sedasis was. With Sedasis, it literally took 5 seconds to set up the propofol infusion, and I'm not exaggerating that. You took out the disposable, went and pull it out, and then you took an amp of propofol and just put it on the spike, and you were done. That was all you had to do.
Okay, I got the link here.
All right, so for everybody, the link that Eric is posting is a link to the presentation. It's a little bit big. It's about 20 megabytes, which is why I can't just email it to everybody. but this is a link to Microsoft OneDrive. That's it.
Yeah.
And so if you click on that link, you'll be able to get the presentation. And it's not confidential. It's freely shareable. And by the way, this is a bespoke presentation. I've never given this talk before, but Eric thought it'd be interesting. So it's a bespoke presentation put together for the meeting today.
I think it's been extremely interesting. I mean, I was not aware of the impact that gas anesthesia can have on the environment. So I think it's a very, very interesting topic, green anesthesia. That's something we need to look more into.
Yeah, if you look at the contribution that as anesthesiologists we could make, it's like getting 1 million cars off the road. I mean, it's huge.
Yeah. No, it's a huge impact.
All right. So we have 5 more minutes.
Can I ask a question? Can you hear me?
Of course, I can hear you. Yes, thank you.
Sorry, it just might be quicker than writing something.
Yes.
When you say you don't have TCI, what? I'm from the UK. I can't imagine that you don't have TCI.
So it's a long and painful story, but the bottom line is that the FDA was ignorant about the pharmacokinetics of TCI. There were people at the FDA, the medical reviewers, who had bizarre beliefs that TCI somehow made anesthesia, that the variability of anesthetic drugs was amplified by TCI. And the rationale kind of went like this. You look at the concentrations that you get out of TCI, and if you're predicting, let's say, a propofol level of 1, the concentrations might be as low as 0.5 or as high as 2. And so TCI clearly is, it's not predictable. And the reason that's a stupid argument is that it doesn't matter how you give the drug, the variability in pharmacokinetics is the same no matter if you give the drug by a syringe or TCI. The pump doesn't change the relationship between dose and concentration. And for every other infusion device, they'd say, boy, these infusion devices are accurate to within 5%, but TCI isn't. But that's because for the other ones, they're actually looking at the volume that's delivered, and said, yeah, well, the TCI delivers volume just as accurately as any other infusion pump. But somehow, in the case of TCI, the FDA was confused and they folded pharmacokinetic variability in to the pump. But in fact, and I've written a paper on this that's highly statistical, but it shows that in fact, the variability with TCI is less than the variability with bolus injection. The most variable kinetics that you will see, the most variable concentrations are after a bolus injection. But I'll ask you, when you start a case, you don't know the intersubject variability. And frankly, your typical induction dose works just fine in like 100 out of 100 cases. So the FDA trying to hold the TCI pump accountable for the pharmacological variability of the drug makes no sense. And because the TCI can incorporate patient covariates, height, weight, sex, and can adjust the infusion rates to account for accumulation of the drug in the periphery, it clearly reduces the pharmacokinetic variability better than any other method of drug delivery. So it's a matter of educating the FDA. I will say that was 25 years ago that those conversations happened at the FDA, and the companies just gave up. But now, with literally tens of millions of uses of TCI around the world and truly zero issues related to the pharmacokinetics per se. I mean, yeah, the pumps jam, they lose power, the batteries short out, the stuff that happens with infusion pumps. But there have been no problems with the TCI aspect of drug delivery over 25 years. And so there's a thought that the FDA might actually be willing to look at data. And that's why I think that if we go back into the FDA, we have a reasonable shot at it. But yes, it's not approved in the United States. Hard to believe since a lot of the technology.
Yeah, so I had no idea. That is very hard to believe. While I have your attention, sorry, do you mind if I ask one more question?
Of course. No,
one of the reasons I've been always slightly resistant to TIVA, although I think I might have been convinced after this talk, is that I quite like having an absolute measure of my gas. So it's really reassuring to say that I have this much gas in my system because I'm actually measuring it. Do you think there's any way, I mean, and BIS obviously just measures depth of anesthesia. Is there any way, do you think, that we could measure propofol concentration in any way?
Yes, we're running out of time, so I'll quickly say yes, we can, and it will not help you. And I've actually studied this. I think that having done the analysis, I then, we published it as a book chapter, but we should have published it in the peer-reviewed literature. But you learn almost nothing by measuring either the exhaled concentrations, which is possible, or the blood levels beyond the actual effect site simulations from the pump. The effect site simulations actually predict patient responsiveness better than the measured concentrations. Kind of a phenomenal thing, because you'd say, how could that possibly be the case? And that's a long explanation, but basically it's because the effect site takes you directly into the brain. Yes, you can measure your gas concentrations, but you know that your patients don't go to sleep until your end-tidal concentrations are about, let's say, 0.6, 0.7 Mac, but your patients don't wake up until the end-tidal concentrations are about 0.1 Mac. So what's going on? And the answer is end-tidal is not the brain levels. With the mathematics, you can actually get right inside and look at the brain, and that proves to be very advantageous. So, so there is a benefit, and the measurement is not as important as you might think.
And you can have a direct measure with a processed EEG measure, like the Connox monitor, where we measure depth of anesthesia directly.
Yeah. Product placement there. I need to disclose Eric's COI. But yes, so that's why I measure drug effect, because like measuring drug effect kind of tells me where I am. And some patients do require a lot more, and some patients do require a lot less. So it is more variable. By the way, I keep looking to the side, but that's because that's where my clock is. Possible to end after this question? Yes. But thank you for your questions. I appreciate the discussion, and I'm honored to be here. So with this, I'm signing off, and looking forward to the next session. Thanks, everybody.
Thank you again. Thank you very much.
Thank you.
Stephen.
Bye.
Thank you.
Thank you.
Bye-bye.
Thank you, Stephen.
Bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you very much.
Thank you. I feel like Queen Elizabeth.